Hello everyone, I'm Ravindran, a faculty in Computer Science and Engineering at IIT Madras. I also head the Robert Bott Center for Data Science and AI at IITM, one of the largest interdisciplinary AI centers in India. So the center started operations back in 2014 as an interdisciplinary lab for data science, wherein faculty from 6 different departments got together to start this group. And we started off small scale with 3 projects. And today, so we are the Robert Bott Center for Data Science and AI. We started operating in this avatar in 2017. And now we have 28 faculty members, more than double our size, across 10 departments in the institute. And so we have more than 120 plus publications in the past few years, and as well as run 23 different interdisciplinary projects. The various areas that the fundamental research areas that the center looks at, right? So we are having a significant focus on looking at data science and AI applications in various engineering disciplines. And network data is something that arises often both in engineering disciplines and across other areas such as biology, transportation, social media, telecom, and reaction networks. So the idea here is that you're not looking at entities in isolation, but looking at interactions between entities as well. And so we have, our center has one of the largest groups in the country that looks at network data across different disciplines and also take advantage of the synergies that arise. So we also have a very large group that looks at deep reinforcement learning. And so we have certainly published extensively in the last few years, and we are the largest group in India in deep reinforcement learning. And we also do a significant amount of work in explainable AI. So we have people who work on explainable visual classification and looking at explainable power of attention in language processing and looking at the dynamics of learning in deep networks. Also learning on interpretable small models and interpretability in healthcare and other specific applications in manufacturing domain and so on. So the other areas that we work on are looking at social impact of AI, causality, both from a process modeling point of view as well as more classical AI notions of causality. And robust learning, learning with guarantees, and learning with limited and partial data, which often arise in engineering disciplines, and also human in the loop learning, where the human is either an expert or could be just an operator who's trying to interact with the AI system. So as you can see that many of the themes of fundamental research arise from looking at specific application verticals. So we have groups that work on manufacturing analytics, financial analytics in collaboration with the DART Center, and also systems biology and healthcare. It's a good fraction of the work that happens at the center is on systems biology and healthcare, and that's in collaboration with IBSC, another center here. And we also do a lot of work in smart cities. We started with looking at traffic, right? Traffic engineering, and now we look at general smart mobility, water distribution, power grids, and also construction, pollution, various aspects to do with smart cities. And so we just not do these kind of fundamental research work. At this point, we are starting to make an impact at the global level as well. So some of our recent work, for example, GrabQC, which is query contextualization for automated coding in a medical domain, won the Best Application Paper Award at PAKD 2021 recently. And before that, we had a paper on explaining deep convolutional nets for image classification that won award at WACV 2020, one of the top vision conferences, as the Best Paper Award. And also at CODS-COMED, a conference organized by IKDD. So we had a paper that won the Best Paper Award for work on class and balanced learning, and then this continues. So in AMAS 2020 last year, we had a top 4 recognition for a paper that used reinforcement learning for discovering structure of social networks, unknown social networks. And then we had a best applied paper runner-up in CODS-COMED on our work with for-hire vehicles. And more recently, one of my colleagues worked with collaborators in Stanford was accepted at Nature Communications on looking at applying network science and control theory to understand dynamic brain circuits. So apart from these kind of research impact, the work at the center is also have significant societal impact. So we collaborate with multiple governmental bodies as well as NGOs in looking at several socially relevant projects. For example, we helped the Tamil Nadu government set up the CM helpline, and also we work with closely on the COVID war room currently. Right? And you can learn more about our socially relevant work at our blog. Right? So continuing with our focus on social relevance, we also launched a fellowship on AI for social good for early career researchers. It's funded by the Narayanan Family Foundation. And so it's a very attractive benefits. Please look up the advertisements online. Right. So we have also contributed significantly in terms of number of tools and data sets that we have released. Samanantar is a large Indian, the largest Indian language corpus that has a parallel corpus that has been released so far. It's done primarily by the AI for Bharat organization, but supported by the Robert Bosch Center. And we also have other data sets such as the Indian traffic data set of HETRA. It's a small data set, but carefully labeled, and also multiple data sets across the different biological problems that we have studied. And RBCDSAI, apart from getting involved in fundamental research, we have also launched several first of its kind programs. Right. So the first one, at least in academia, this is the first such program, the post-baccalaureate fellowship, wherein we give a 2-year research fellowship for exceptional graduates and postgraduates. And this is modeled after some of the programs that the top-notch research labs in the country have. And we have had significant success. We have had about 14 post-baccalaureate fellows so far, and many of them have produced excellent work, excellent research that resulted in top-notch publications, and some of them have turned around and joined us, and some have gone on to do PhDs abroad. And we also have this interdisciplinary dual degree program in data science. We are the first IIT to launch a degree program in data science, and where the graduates get both the BTech in engineering discipline as well as an MTech in data science. And the focus is on training them in applying the data science ideas to their parent discipline. And we also have this 11-month certificate program in collaboration with IIM Bangalore, which straddles both technology and management. And we have launched the industrial consortium model, wherein we get partners, industry partners who work closely with RBCDSAI and partner with in various events that we run at the center, right? So that they can get more exposure to the kind of research that happens here, and also this leads to better dialogue. And we have had excellent feedback and enthusiasm from the consortium partners so far. And we also have launched an associate researcher program, wherein we allow people or invite people from the industry labs as well as from other institutes, like some of the newer IITs, to associate themselves with the center, and so they get to co-advise students, we get to co-write project proposals, as well as take part in some of our workshops and other programs that we run. Right, and this is a fellowship spread over 2 years, and we have had multiple very interesting outputs come out of this already. So here are some numbers. So like I mentioned in the beginning, so we have about 28 faculty spread across 10 departments who are part of the center. And we have about 80 plus researchers, 6 of them who are postdocs, and about 10 post-baccalaureate fellows are there currently, and about 50 plus research scholars, both at PhD and master's level. And as I mentioned earlier, we have 120 plus papers that have come out, of which more than 50 have high impact conferences, like A-star rank conferences and very high impact factor journals. And we have collaborations across the board. This is like just the mind-boggling number of collaborations that we have both in the industry and NGOs. And we can also see our international collaboration footprint is fairly large going now. And hopefully we are looking to expand this much further as we go down the years. Right. So one of the new research initiatives that we have launched this year is looking at what we call as deployable AI. So doing AI research in the laboratory is fine, but when you actually try to deploy it in the field, a lot of things that could go wrong. So we are looking at it, multiple facets of this, looking at fairness and social relevance of AI, explainability, transfer learning, right, and also privacy and safety in AI, and also AI on the edge. Right. So this is when or like federated learning. So where you want to make sure that your distributed AI systems work great well in synchrony. Right. So there are multiple projects that we already launched in this theme, right? So we are looking at AI and ethics in the Indian context, especially looking at notions of fairness in Indian context, and also looking at how deployment of AI could further marginalize populations which are already suffering due to the digital divide in India, right? And then we're looking at various interpretable models and algorithms for human-in-the-loop learning. And so this is essentially where the human should understand what the AI is doing before they can react to it. And then we have fairly a couple of projects that are running on interpretable deep learning, especially in the context of healthcare, and also looking at incorporating domain knowledge in an interpretable or explainable manner into machine learning models, so that domain experts are having a slightly increased comfort level when they are looking at the prescriptions of the machine learning approaches. Right? So there are multiple ways in which you could work with us. Right? So we have the postbaccalaureate fellowship, as I mentioned earlier. We also do multiple internship program, including a global summer internship program, and the fellowship, that's a postdoctoral fellowship, as well as the RN family fellowship. And we also have a new certificate program that we launched with Talent Sprint. So please look that up. And RBCDSAI is on social media and is on the web. And please look up our YouTube channel, our Twitter channel, and everything for more information about us. So do write to us if you're interested in joining us or interested in knowing more about the center. We always welcome that. Thank you. Hello, everyone. I'm Ravindran, a faculty. Hello, everyone, and that's me again. I was on recording so far, and now I'm actually in live. And so today, you must have heard me mention about GrabQC, and so today's seminar is all about the work on query contextualization, and it gives me great pleasure in introducing the speakers of the day. So the first speaker would be Sudarsun Santhiappan. So Sudarsun is a very old hand and very familiar face at IIT Madras. He did his master's here at IITM a long time back, and then has nearly 20 years of experience in the industry now, developing various kinds of very, very interesting cutting edge solutions. And I have known Sudarsun, God, from 2005 now. Yeah, so I've known Sudarsun from 2005, and he's currently working on his PhD with me as well. But more importantly, he's also very passionate about doing research here and developing solutions within the Indian ecosystem. And even though he has had multiple opportunities to leave, he has not. And so that is something that I would hope a lot of people here can actually emulate as well. Right. And Sudarsun, so thank you for agreeing to do the seminar. And the other speaker is Jeshuren. Jeshuren did his undergraduate from Tyagarajar College of Engineering, my alma mater as well. And he joined here for an MTech and then continued to work on a PhD with me. And he's also currently working at Buddy.ai, the company co-founded by Sudarsun. Right? And so both, it's doubly happy that, I'm introducing both my students who are going to give this talk. So over to you, Sudarsun. Please, you can share your slide.
Thanks very much, sir. It's an honor to be here. Okay, so hello, everybody. So the next several minutes, we are going to share some of the experiences that we had in solving one of the most important problems in the healthcare space. So I'll set the context so that you understand why we did it and why such a problem needs attention, and what is the impact of the outcomes of a solution of this type in the healthcare space. And this solution, it's a paper and it is also in production. So we have built products around this idea. And as we speak, people use this solution to solve problems in the real world. So with that pretext, let me start. So the title of the topic is AI-powered medical coding for electronic health records. So I'll just give some introduction about what is electronic health record, just basics, the fundamentals. So in the Indian setting, a medical report. So as we speak in India, when we go to a hospital and you get a report at the end of your visit to a hospital, and we call it the medical report. And most of the times it's a printed document. There will be an electronic version of it, but the hospital usually does not share that with us. And they keep it in their archives. In many of the situations, the record that Indian hospitals create are handwritten. So they say that around 80% of the documentation created in the Indian ecosystem, healthcare ecosystem, is still non-digital. So it's a great opportunity, actually. You see, in the US, it's 100% digital, and it's a crime if you write something in handwriting and prescribe to a patient. It's a crime there. So everything is digital, and everything is electronically stored and transferred and manipulated, processed. So that is called an EHR in short, which stands for electronic health record. So the health record keeps track of what has happened to the patient and what are the various services, or what are the various medications that are given to the patient. It's basically a complete history of a particular patient. It can span across several episodes over several years. People maintain that, right? Hospitals maintain all episodes of medical information about a particular patient. So medical coding is a task, right? So medical coding is an interesting task, which was originally introduced to simplify reading a medical chart. I'll tell you where we have to read a medical chart. And physicians do it day in and day out, because they have to understand what is the history of a patient, to understand the use case better, so that they can give quality treatment to a patient. So they have to read it. But other than the physicians, who else would read it? So there is a group of stakeholders who read medical charts day in and day out, which is the insurance companies. So when a particular medical procedure led to a cost to a hospital, and if a patient is covered by the insurance, it could be personal, it could be state, it could be central insurance, anything, the insurance company has to sanction that money, whatever that has been spent on the patient. So the insurance stakeholders, we call them as the payers. So the payers are reading medical charts day in and day out. But the problem here is medical charts are verbose, right? They are very, very long. An inpatient medical chart can run into hundreds of pages, trust me. An outpatient chart, in India, we don't have outpatient chart. We just get the RX, which is the prescription. But in the US, there is an outpatient medical chart also, and that can also run into multiple pages. So reading a medical chart for processing insurance claims can be a very costly affair in terms of effort and time taken. I'm sorry about the noise. I'm co-sharing my space with my dog. Sorry. I will try to be louder. Right. So it is absolutely necessary for the insurance company to process the document faster, so that the settlement of the claims can happen faster. In the US, it is mandated that all claims be settled in less than 3 months' time. In India, it takes more than 6 months, by the way. We don't have any upper cutoff here, but there is an upper cutoff of 90 days. So you will have to process all the claims in less than 90 days. So if you end up spending reading all the documents, and it's impossible to satisfy that TAT, the turnaround time. So the process of medical coding was introduced to cut short the time taken for somebody to read and understand the document. So essentially what we do is we codify, next slide, we codify a document, and we codify the document into different interesting aspects of the document. So a medical chart essentially covers 2 or 3 different important aspects. One is what is wrong with the patient. So that's we call the diagnosis. And there is a taxonomy which captures that information called ICD-10. And there is another taxonomy called CPT, which captures the information about what has been done to the patient to address that medical condition. So these are the primary information carriers which actually represent a medical chart in just few quotes. So instead of looking into 10, 15, 20, 100 pages, you just have to look at few codes. Each code has a specific meaning. And if you just know the codes, and that is more than sufficient to understand what went wrong with the patient and what has been done as compensation to that in order to do the correction. And of course, there are some other allied codes like, what are the consumables? So did you use a wire gauze to fix a cut, or did you use some additional medical equipments to provide services to a patient, so on and so forth? So those are covered under another coding taxonomy called HCPCS. So that's a small part. And essentially, when a claim is submitted to the insurance company makes the payment based on CPT codes, which is the services offered by the hospital to the patient, but it is contingent on the ICD codes. So ICD codes are super critical, very, very critical. And the accuracy of ICD codes, there is no compromise. So the maximum error that we can have in codifying the documents is maxed at 5%. So the maximum error affordable is just 5%. So the expectation of a system which does medical coding is supposed to guarantee that 95%. And so far, in the last several years, medical coding has been 100% human-powered process. And Buddy is one of the front runners, and Buddy-like companies are trying to automate the medical coding as a process in order to speed up the overall revenue cycle management workspace or the space. So RCM in short stands for revenue cycle management. That is the conglomerate of all the processes that undergoes or that happens between the hospital and the payer. Hospital is called the provider. The insurance company is called the payer. So all the transactions that happen between a hospital and a payer for settling a particular claim, these are all covered by the RCM space. It's a very, very large space. It's $1 trillion market. And medical coding is one of the very important functional blocks in the RCM space. And let me move forward now. So far it has been done in a manual style. So how do we do it in an automatic style? So automatic style, there could be several ways of addressing this problem in automatic style, but there are some certain challenges. The challenges is that, let's say if I use machine learning to solve this autocoding problem or medical coding problem, the first question anybody would ask is the system explainable? Because all these days, the answers are all the all the medical codes that the humans had assigned for a medical chart are all explainable. If something goes wrong, it's very easy to do RCA and who did it, which company did it, which batch of documents went wrong. Everything is traceable, right? And all these are in place. The processes are in place. But when we swap out manual processing with machines, which are AI-powered machines, how do you guarantee explainability? And with the latest deep learning tech, explainability is still a challenge there. I mean, a lot of models are not naturally explainable. So we'll have to do some extra arrangements to provide the necessary explainability which a client would seek. The second challenge is the availability of label data. So there is availability of label data because all these days humans have been curating these data, but the problem is they won't share it with you. Right? These data contain the patient identifying information. So there is a stigma around sharing healthcare data for AI research. And I think that is one of the reasons why AI is still in the nascent stage for the healthcare deployments. In all other deployments, AI must have been really matured or is already matured in a lot of spaces. But in healthcare, we are still in the early stage because of the stigma around sharing data with AI practitioners. And so it's very hard to acquire data from a hospital or acquire data from an aggregator. So availability is a challenge. There is data with all these CIOs, but they will not give it to you. It takes a lot of negotiation to get data from them. So at Buddy, we have access to a lot of data, and we are in the market for the past 8 years now, and we got our first dose of data after 18 months. So it is that hard to acquire data. But right now, we have a lot of data at our disposal, which allows us to do research. And the third most interesting problem is the label space. The label space itself is a problem. So if you look at ICD, which I said is the critical piece, has around 72,000 codes. It's an approximate number. It can also be larger than that if we include the minor variations to it. Right? And the space is large. So it is not like, I get the data from somewhere and I just pull in some existing machine learning algorithms and I can build a classifier in no time. It is not that simple, right? It's not that simple. So we'll have to think about a lot of other things when we look at these kind of extreme classification settings. Right. So what we did to solve the problem is to look at the problem as not as a fully machine learning powered process. Rather, we wanted to conceive this as a hybrid system. So the hybrid system means it will be majority of the load will be taken by statistical machine learning systems, and a larger chunk, a sizable chunk of the task will be powered by human intellect, which we call the knowledge-based systems. Knowledge-based systems are perfect because they are 100% explainable and they are very accurate. The only problem is they are not scalable. You cannot scale a knowledge-based system, which is with human intellect, and a rule-based system to solve problems. It's very, very hard to scale. But machine learning systems are very easy to scale, but they are not very accurate. So we are trying to get the best of both worlds and conceive an hybrid solution. Right. Next slide. So I'll tell you what is the impact of autocoding in the business world. So right now, over $265 billion are wasted. in doing manual processing and various caveats in manual processing. And 42% of physicians complain about burnouts because they are overwhelmed by the documentation workloads. Instead of documentation, their time is better spent with the patient. So we have to introduce automation in every aspect of healthcare to save physicians getting burnt out. And the biggest challenge is 80%, 67 to 80% of the data coming from the healthcare world is all unstructured. So AI for unstructured text is always a problem. And it's one side it is a problem, but the other side it is also unlimited availability of challenges. So researchers like us should get really excited when we see problems like this, because this is an opportunity waiting for us to go and explore that. And when it comes to claims, because of coding faults, 34% of the claims are getting denied, right? Coding, medical coding or auto coding, or people make mistakes when they do medical coding. As I said before, only 5% tolerance. Only 5% error tolerance is available with us. And despite that, there is 34% denials, which means the hospital has spent the money, but hospital will not get the money from the payer because they made a mistake in filing their claims. And there are several other reasons for why we should do autocoding, right? Next slide, please. So let me put the problem in a simple mathematical way. So what we have is we have EHRs, which are free running text documents. And our objective is to put this into an appropriate bin, which represents a set of codes. So in short, this is a multi-label classification problem. It's a multi-label classification problem. And ICD is a multi-label classification. CPT is a multi-label classification. HCPCS is also a multi-label classification problem. And we can look at it as a way to map the contents of an EHR to respective codes from the standard taxonomies like ICD-10. Next slide, please. So next slide. So our motivation, why are we really motivated to get into this GrabQC idea? So what we did is we said, okay, we want to do the hybrid approach, but what should we do about the hybrid thingy? So what we wanted to do is to mimic what medical coders, the human medical coders do to solve the problem. So we want to borrow the ideas from how they understand and process the data to get to the final codes with 95% guarantee on accuracy. And we just want to borrow the insights. And we said, okay, why don't we put that insight into our machine learning equipment and try to give similar effects, right? So we actually sat with the medical coders to understand how they do medical coding. So interestingly, if you see, for specific taxonomies, there are specific regions in an EHR which actually twinkle, I would say. We don't need to read the entire chart. So if you give an EHR which is running 10 pages to a medical coder and ask that coder to do ICD coding, they'll probably come back within 30-40 seconds because they know where to see and what to see. Both parts are there, where to see and what to see. So where to see is basically the section of the document. Which section of the document should I go and see? And secondly, after you landed in the section of interest, what are you actually looking out for? What are you hunting for? So what are the different features that you want to see in the document so that you can translate those features into ICD codes? So this is exactly a deep learner would do. So the equivalent of that is attention in the deep learning world. So we actually discover the importance, where to see and what to see. All these problems can be modeled as attention. This could be soft attention or hard attention, but it is a form of attention. It can be modeled. So we got this idea from talking to medical coders, sitting with medical coders and see how they work in solving the medical coding problem. We borrowed these insights and we put that insights into our machine learning equipment. And that's how we were able to pull it off, right? And the third thing that we observe is that the medical coders follow a standard dictionary for solving their day-to-day activities. So there are standard the standard tools powered by 3M, Optum. These are like market leaders in the medical coding space, but none of them solve autonomous autocoding like what Buddy does. But these products or these companies are the market front runners when it comes to helping medical coders to expedite their work. So what they do is called CAC, computer assisted coding. So the computer provides extra information to the medical coder so that the medical coder need not remember everything. They just have to look at the most important areas of a medical chart and connect the dots between various available information there and translate the connected information to a medical code. So that's called the assisted coding. So 3M, Optum, like companies, they have products. One product is called Supercoder. So it's an Optum product. So Supercoder, you will see every medical coder will be using it. You will see one window with Supercoder. So when they see a particular medical terminology, they just put that in the supercoder, and supercoder will tell you what are the possible code matches. And based on the code matches and based on whatever they see in an EHR, these guys take a decision on the fly to assign the particular code. So this is the background of how medical coding happens and what are the opportunities that as machine learning scientists like us should learn from the existing workflows and incorporate them into our machine learning equipment and implement and roll out a solution. So with this, I'll stop. I'll hand over control to Jeshuren, and Jeshuren will explain you how actually we pulled it off. So I told you what are the information that we borrowed from the system. Now Jeshuren will help you understand how that information translated into an actual product, an algorithm, which actually works. So over to you, Jeshuren. Thank you.
So thanks very much for the very broad background and the motivation for the solution. So I would directly delve into the solution on how we pull this off. So as we said, so we wanted to construct the system as a hybrid of deep learning and information retrieval based approaches. So what we did was we pulled it off as a clinical information completion problem. So what I mean by clinical information completion is we take some incomplete pieces of text from the document and we try to complete it automatically. So we have three important contributions from this work. So one is the entire system, GrabQC, which automatically extracts these queries from the document and contextualizes it based on other information present in different sections. And then we also use the graph neural network based approach, which would go over a constructed contextual graph and picks out what are the relevant nodes, and it does it by training over a large corpus. And then we also introduced a distance supervised method that we use to train the graph neural network. So I will go into details of all these three in the next few slides. So this is the outline of the proposed solution. So what we have here is that, so we have a clinical text as input, and we want to give the corresponding ICD code, which is the required output. So what we do here, so we do a mixed batch of deep learning and IR-based approaches. So we use the GrabQC system to get a contextualized query. And now this contextualized query is converted into its corresponding ICD code using the information retrieval system. So now this, you can visualize this IR system as something like Google, wherein you go in and type a query and the corresponding results come out. So this is how we do it. So first, what we did is, as we talked about the different sections in the piece of a clinical record, we sat with the medical coders and understood what are the sections they primarily look at to arrive at this ICD code. So here in this clinical text, we have this clinical impression section, which documents the important diagnosis made by the physician on the patient. So in this case, the physician has documented that the patient had come in for a abdominal pain. So here, if you look at the query, it doesn't contain more context. So by context, I mean like in which laterality or which region of the abdomen the pain had occurred. So when this translates into a ICD code, you won't get the best possible match. So we need to get other important information which is present in the other pieces of text. So that's where we use the named entity recognition module, which would extract some named entities from these other parts of the text. So here, if you could look at the NER parser has identified different named entities like the lower quadrant, the pain, and different other entities which might be of interest. And one other thing that we did was to link all these entities to a standard knowledge base. So we did this linking to alleviate the problem of polysemy and synonymy. So there might be multiple ways in which medical concept can be referred, and there are different ways in which the physicians record these concepts, and So to maintain a standard, we did this linking with a knowledge base. So once we have these set of entities that might be of interest, and we have the initial set of queries, it is like contextualizing this query using some graphs that we generate. So what we did is, so we have these information which is extracted, and we have these entities that have been extracted from the other parts of the text. So what we do is we go over each sentence and find if there is a link between any of these entity and an entity present in the query. So here we see that there's a mention of pain, and also there's a mention of pain in here. So we add an edge between these entities. And what we also do is we add edges over other entities that are present in the same sentence. So here, if the sentence in here is the pain is intermittent and tends to be worse with movement, and also the patient presents for an evaluation of an abdominal pain, radiation to the back. So what we do is we associate all these entities with the other entities that are present in the same sentence. So once we do this, so what we do here is we get a contextualized graph which contains edges between the entities in the query and the extracted entities. So if there is a path between these extracted entities and the entities in the query in an external knowledge graph, we add an edge between them. So in the same way, we do it for all the entities, and we arrive at a contextualized graph. So in this contextualized graph, what we observed was that there was some other information which might not be pertinent to ICD coding. So there were information like the abdominal pain got worse with movement, and the patient had some diarrhea, episodes of diarrhea. But these are information that are relevant for some other tasks, but they didn't match our current task in hand. So what we wanted to do, we wanted to automatically find what are the information that are relevant and what are the information that are not relevant to our current task, which is ICD coding. So what we did was we framed this as a supervised learning problem, wherein we gave this contextualized graph as an input for a graph neural network. And it was the, we trained the model, the graph neural network model, to automatically predict what are the relevant nodes and what are the non-relevant nodes. So in this case, if you see in here, if this graph was given as an input, the model was automatically able to label the ones given in green as relevant nodes and the things that are not needed as in red. So how did we do this? So as I said, this was a supervised learning problem, and we used a feature representation for all the words that are present in the each node as its initial feature embedding matrix, and then we passed it to a graph neural network to get the final representation. So I will skip these important, so we will skip these modeling parts so that we get time to come to it in the later slides if there is any. So once we have these important or relevant information that have been picked out, so we concatenate all these information into a query, which we call it as a contextualized query. So now, starting from a normal seed query, we arrive at a contextualized query, which has more information about the diagnosis. So once we have this contextualized query, we pass it to an IR system to get the final ICD codes. So here we pass it to an Elasticsearch system, which predicts that the corresponding ICD code for this diagnosis is R10.31. So that's the model wherein we went from a clinical text to a corresponding ICD code. So one thing that is more pertinent in here is how do we get the data, training data for node classification. So as we have seen, so the training data that is available is present at the chart level, wherein for every clinical node that is being presented, we have a set of ICD codes. But to train the GNN model or the graph neural network model that we talked about, the level of supervision was needed at the level of nodes. So we needed node level supervision for this task to be happening. So what we did, we used a technique called distance supervision, wherein we used the descriptions of the node labels that were available during training time, and we tried to do a similarity match between the descriptions of the ICD code and the constructed contextual graph. So if the similarity was greater than a threshold, we said that that node was relevant for the ICD code to be predicted. So in the same way, we did this for all the contextual graphs that were generated automatically, and we were able to generate labels for free of cost. So that's more about the solution. So I will quickly walk through the different experiments we did to evaluate the usefulness of our method. So what we had was we had access to two different anonymized data sets. So one was a subset of the mimicking data set. So this is a publicly available data set, which contains the ICU discharge summaries. And then we had access to EHRs from a hospital's emergency room. So these are the statistics of the data that we used. And another key implementation details were the knowledge base that we used for linking these concepts were UMLS and SNOMED. And then we used an off-the-shelf model from SkySpacey for NER entity linking. And all these IR systems were implemented in an Elasticsearch framework. So we used PyTorch for training all the deep learning models. And during experiments, we found out that there were some keywords that were occurring in the description of the ICD codes, but they never occurred in an electronic health record. So something like the pain was unspecified, or the pain occurred NOS, which means not observed or something. So we tracked down the top 4 external keywords, as we call it, and we added them as nodes to the contextual graph that was generated. So, and we let the model pick whether it was relevant or non-relevant. So coming to the experiments, we wanted to first evaluate our choice of a graph neural network. So there are different types of graph neural networks that are available. So one is the most famous graph convolutional network, and then we have graph attention network. And then for this method, what we used was we used a higher order graph neural network, which contains skip connections between these different layers. And what we found out that the choice of GNN, or the model of GNN, which we used of a higher order, which aggregated informations from higher order neighborhood, was performing better than the other two models. So the reasoning that we give for this is, since the root node or the center node for our contextual graph is the important query that we extract from the clinical record, and if we add more information across these different layers without the information being passed on to each layer, then the noises take over the important information. So that's where the skip connections in the GNN helped us to get a better picture, and we were able to get better results while using other methods. And the second experiment we wanted to do it is, like, we have some query that has been constructed. So we have this contextualized query. So how does it compare it with the query that we automatically extract? So we have some C query. How does it compare to that query? And then we have a query which can be generated from the contextual graph, which contains both relevant and non-relevant information. And then we have the query which is being generated by GrabQC, which is only based on the relevant nodes. So when on comparison, we found out that the queries that were generated using the GrabQC method and the ones that had the external information were performing better than the other two levels of queries that we had. And the third experiment that we did was, since this was a multi-class and multi-label problem, we wanted to compare it with other different methods that were already present in the literature. So what we did, we compared it with a CNN-based encoder, and we also did the same with the LSTM or a by GRU-based method, wherein the input was the whole clinical text and the model had to predict these different codes. And we also compared our model against specialized architectures which were used for automated ICD codings. And so CAML and multi-res CNN are such architectures which were specially designed for automatic ICD coding. And we were able to see that our method was able to beat them consistently at all different metrics that were considered. So now we also did some analysis on what are the number of layers for the GNN that would help us get the bigger scores. And we found out that 3 was the optimal setting. And one more analysis that we did was on the qualitative side. So till now we were seeing the quantitative results, and we wanted to see how the results qualitatively improved when we had the contextual query in place. So this was a normal query which was extracted from the clinical note, which just said about a particular condition. So we never know what happened, in which region it happened, or in which laterality it happened, because these ICD codes greatly differ based on the place of occurrence or the laterality of occurrence. So here in this cases, if you could see, we had this condition, but our contextual query was able to extract that it had happened on the right lower back. And another important case is this query missing the importance of laterality. So here we have the laterality information that is being present. So the same is the case for all the other queries. So this is the proposed work and the results that we have from our work. So I just wanted to quickly go over some of the other related work from literature that is available. So as I said, the research community is always looking to solve these either as a machine learning problem or as an IR problem. So automatic ICD coding has been solved as a multi-label classification problem, wherein they try to extract some ML-based features from these clinical notes or using some deep learning encoders. And some works have also looked into adding these hierarchy of ICD codes or the label descriptions. And there were also works which use graph convolutional networks to find out the correlation between the hierarchical relationships among these ICD codes. And there were also informations that were extracted from freely available knowledge bases like Freebase, and they tried to incorporate this knowledge as part of the training and let the model decide whether to include these information or not. And another view of solving this problem is to treating it as an information retrieval problem, but there hasn't been very much great success on these sides. So there have been like very few works which tried to solve this as a KNN-based problem, wherein the document was mapped into an embedding space and the nearest neighbors were chosen for getting the relevant codes. So to finally conclude, so what we have done in this work is we have proposed a process that can automatically go from a clinical record to a set of ICD codes that can be used in the process of billing and other stuff. So we have proposed a system which can automatically do this, and we also have some interesting results on the experimental side which propose the effectiveness of our method. And in the future, what we plan to do is we plan to use the reinforcement learning to extend this method and get away with the process of distance supervision. So now distance supervision provides us the label. So can we use reinforcement learning to automatically find out what are the nodes that are relevant or not? And one more thing is we want to use this as hard attention for DL-based methods. So can these relevant information that has been extracted be used as hard attention? So that is some ways that we are trying to looking forward to extend this work. So I'll stop here for questions. So thanks everyone.
Thank you, Sudarsun and Jeshuren, for a great talk. Let's see. Okay, so if there are any questions, please post them in the Q&A panel. And if the panelists have any questions, please feel free to unmute yourself and ask the questions.
So there is a question on the QA from Dr. Juby George. Is this research help to globally share the treatment and diagnosis detail? Can they speak up? Is that allowed, Professor?
Not yet.
Okay.
He has also posted a second question if you want to take that.
They're connected, I think.
Yeah, is it possible to access it? I think the question is, are the results of this research available globally?
Yeah, absolutely, yes. So the paper is in the public domain, Doctor. So you can actually have a look at it, definitely.
Let me figure out. Okay.
Okay, so another question which says, what is the approximate time to process a clinical document of 10 pages? So usually, okay, that's a good question. I'll just expand it a little bit. So when medical coding as a task is given and the usual TAT is 1 day, the turnaround time is 1 day. But so we give a 6-hour stat to our existing customers who take our help for autonomous coding. So the 6 hours is not really required for processing a document. So usually we get batches of document, and so the batches will have to be processed in 6 hours. So that is how we should see it. But if you look at a per document timing, it is in an order of few seconds when it comes to autocoding. But GrabQC is much faster than that. Jeshuren, you want to comment about the approximate milliseconds that it takes to do something with GrabQC?
Yeah, sure. So with whatever experiments that we had done, so the amount of time it took never crossed a second. So it was like in milliseconds. Yes.
See, the GrabQC is a micro task. See, GCN and all these graphical graph-based neural networks, they are extremely fast because they use GPUs to do model learning, and they can also use GPUs for inferencing. So they are extremely fast. So there is we don't have to really worry about the speed issues. Usually, deep learning inference task is very fast. Maybe the model building is relatively slow, but inferencing is usually very fast. So it's in an order of few milliseconds. But what we do in production is we set a deadline of a few seconds per document to finish everything end to end. So document in, results out, it should not take more than few seconds, depending upon the task. So that is the timeline we set up, because the existing distributed platform expects such a timeline. So it will be in tight budgets usually. The time budget is usually very tight. Okay, Jeshuren, somebody's asking you to share the references.
So there's another question on what are the medical specialities that in which autocoding can be used. I mean, is there a restriction to this work, or?
No, it's agnostic. It is agnostic. The autocoding solution itself is agnostic by design. But the thing is, every specialty is unique in its own means. For example, so Jeshuren had run this exercise with the emergency charts. Emergency charts are one of the most complex charts because they document a whole lot of information that happens in an emergency room. So they are usually very long. The longest of charts is from the evaluation and management. So in India, we do this physician visit, right? So when we go to a doctor and do a full body checkup, so the equivalent of a full body checkup in the US is called EM, evaluation and management. These are outpatient. So you go in the morning and you come out after a few hours, but the length of the chart is usually 20-30 pages, usually. So, and the shape of the documents are different across different specialties. So if you look at a radiology report, so the report that when you go to a scan center, they give you a report, right, an impressions document. That usually is very small. It's half page, 1 page. Sometimes it's one-liner also in India. In the US, it is usually 1 page to 3 pages, depending upon what has been scanned and what are the different regions that got scanned. So that's one of the shortest structure you may find. And surgery is another surgery, outpatient surgery, same day surgery. That is another modality of data, which is very verbose in nature. So it is all descriptive, but it usually is short, 2 to 3 pages. So medical coding as a task is agnostic by nature, because what you are doing is you are looking at the rightful place where you will find the rightful information so that you can take the correct decision to translate it to a code. But the structure of the document can be very different. So the direct answer is agnostic. And lately, we are actually exploring some interesting discussions with some prospects where they are asking for multilingual autocoding. So, in fact, yesterday we had a discussion where people are asking, "Okay, can you run this English autocoder for Deutsch and French?" So that was a question we faced yesterday. So by design, it will support, but it takes some effort. So the takeaway is it should be designed agnostic, and we have designed it that way. Yeah, there are more questions.
Yeah, there's one. I'll try to pick out the more interesting ones. You can just answer.
Sure, sir.
So how frequently does the external knowledge base have to be updated?
Good question. Great question. The thing is, it depends on what point you are in your knowledge base maturity. So if, let's say, UMLS and SNOMED are updated every 6 months, usually. So you get an update every 6 months, and that is published online, and it is public domain data, and it is free to download. Anybody can use those data. And lately, there is a very nice package called PyMed Termino. It's a Python package which actually help you to process that large taxonomy in a jiffy. So it makes life so easy. So you should consider exploring that. It's called PyMed Termino. I don't know why they named it that way, but just explore that. So these taxonomies and ontologies are updated regularly by the governments. So every country may have their own taxonomies and ontologies maintained by their Department of Healthcare or Department of Health. So in the US, it's called NLM, National Library of Medicine, and they are the owners of all these data, and it gets updated regularly. And the quantum of updates can be varying, but it gets updated regularly. But when you maintain your own knowledge base, and it depends on what is the addendum you want to add to the database, right? Your store, your ontology, what is the addendum you want to add to the data set? So if you change the knowledge base frequently, it's actually a problem, because all the other systems will get affected. So we actually time it. Like once a quarter or once a semester, we make the updates to the knowledge base. So that will be it. Updating it every day is very detrimental. Hope I answered that question, Professor.
Yeah. I mean, so I'm just reading out questions from the audience. Can we use inferences from I2C2 dataset for Indian healthcare predictions? I'm not sure what exactly they are asking, but can you take
Jeshuren knows, because he's currently working on I2C2. Yes, go on, Jeshuren.
Okay, so I presume that it is I2B2. So
B2, sorry.
Okay, so we have been working on this data set, and so the context in which we are working is to identify the personal health information from these medical records, and we see that the documents structure varies from the different countries it comes from. So I don't think since the distribution has changed across these different countries, there's very much of transfer of knowledge that can happen between these modalities. So I don't think we can use them directly.
Yeah, but see, sure. Don't be disheartened by Jeshuren's answer. But the thing is, we'll have to identify what is a task you want to take up for your research. See, the data sets are the person who shares a data set may have a purpose for the data set, but it doesn't mean that is the only purpose. You can actually transform the data to your needs and see what else can come out of that. See, that's the exploratory part of your thinking. You see, whatever you have, what can you make out of it in its best form? That is always in the hands of a researcher, right? It doesn't mean that you have to use it for the purpose for which it was originally earmarked. So we have done a lot of transformations like that when we ran out of data for a specific task. So we use data from cross-functional areas and try to leverage them. So you just have to keep your mind open. That's how I'll see it. So right now we use I2B2 for PHI, so the personal health information. So we are using that data to improve the quality of our PHI identification, because usually when we work on healthcare data, we have to be very, very careful about PHIs. Because if this is very confidential, and when we acquire the data from the original owners, we get into an agreement called Business Associate Agreement. In short, it's called BAA, and that says that me being a partner can have access to their data, and we are also giving a guarantee that we will keep the data safe. So if the data goes out, then whoever has signed the BAA has to face criminal prosecution. So it is criminal. It's not even the regular thing. It's criminal prosecution, right? So it's a very serious agreement that you will have to enter, and we'll have to be very, very cognizant about protecting the confidentiality of everything. So the safest way to do research with healthcare data is to de-identify the data and then play with the de-identified data. So sharing PHI is a crime, but working with de-identified data is most welcome. So what we do is we get the data always with PHI. So we have a data management group which cleanses off the PHIs and replaces them with some random identifiers. That's called de-identification, or it can also chop it off. It can redact it. That is also possible. So depending upon the needs, we do a transformation on the data, and then the data gets floated for others to see. So the PHI is not privy. People are not privy to see the PHIs. Only very specific data management fellows will have access to PHI. So I2B2 was used, is being used for improving our PHI identification in an automated fashion.
Okay, so one final question maybe. Can you elaborate on what is the higher order graph neural networks that are being used in this work?
Yeah, sure, I'll take that. Okay, so if you could see in here, right? So we have these three different kinds of architectures for graph neural networks. So one is the graph convolutional network, which just takes in information from all its surrounding nodes and aggregates them using an embedding matrix to get the final representation on the different layer. So another standard thing is, like, instead of giving equal weightage for all these three different nodes together, all the different neighbors, the model automatically learns like how much importance to give to the neighbors in the first order neighborhood. So this is graph attention network. So another higher order graph neural network that we used for this was to just have the information of the current node intact and also allow for skip connections from the different layers. So suppose if there are like three orders of neighborhood in a graph, so once we have the second layer, the information from the different layers that were previously present were also added to the graph to the final representation of the particular node. So that's why these higher order graph neural network like differentiates from the other two.
Okay. So thank you, Jeshuren and Sudarsun, for taking the questions as well, and thank you for a wonderful talk. So there is one final thing is, so I know that PAKDD proceedings are behind a paywall, right? Do you have an archive version of the paper?
Yeah, I'm planning to do it, so it will be up in a week.
Sure. Well, I knew the answer. I just wanted you to say that. So thank you once again, and thanks everyone for attending the event. And
thanks for the opportunity.
Do check out our YouTube channel for other events and follow us on social media so that you get updates on all our future events. Sorry, over to Sudarsun. Yeah.
Thank you very much for the opportunity. It's an honor to be here to share our experiences, and thanks very much to the audience. You have been very active, and an interactive session is a great bonus for any speaker. So thanks very much for the active participation. Thank you, everybody.
Thank you.
Thanks, Professor, and thanks everyone for the question. Thanks.
Bye.